absorption is showing just where is it absorbing in the UV spectrum. Well, it looks the same in all these different lines, or all these lines, any solvent we can put it in. So oxybenzone really doesn't care what's around it. It's going to absorb the same area of light. That's so interesting. We move to our next compound, just adding one extra group up there. What we notice is we have two distinct regions of light that can be absorbed, and it correlates directly to the type of solvent. If you're in something oily, it absorbs in one region. These molecules don't interact a lot with the solvent. In contrast, if you put it in an alcohol or like water, anything that can have a strong interaction between the solvent and solute, huge shift in the UV. This is actually a pretty decent size shift. So the question now became why? And so about 2 years ago, we started moving in that direction. And this is going to lead directly to what Sarah-Beth then continued with. Our first indication was maybe it's because we have one blue group here, but we have two in dioxybenzone. Something about that OH group. That hydrogen is something that we often refer to as an acidic proton. So acids are species that have a hydrogen that they can give up. So to probe if there's an acidic character to this molecule, what you can do is put it in an acidic environment versus a basic environment and look, does it care what the pH is? And we see if they're in acidic or neutral environments, those types of environments will have that hydrogen on it. They look the same almost. That's these two lines here, and that's those two compounds. If we put it in a basic environment, what should happen is the acid should release its proton. And we see it shift in the spectrum telling us something happened. But how these two look, not the same. So how they respond is different. And this leads us directly to Sarah-Beth's work, which is kind of where we stood about a year ago now. And when Sarah-Beth was looking at her IS projects, as a good chemical physics major, she probably wasn't happy with this qualitative description and wanted to get some numbers. So what her focus is now is to try to figure out then, can we quantify how acidic these molecules are? So compare oxybenzone to dioxybenzone to acetylbenzone, which I didn't talk about. But can we actually quantify the acidity in the lab and potentially in a more green way on computer? So with that, I'll turn over to Sarah-Beth to talk about her nice project, or progress with this project.
Thank you, Dr. So in order to characterize this acidity that she was talking about, it's a molecular constant called the pKa. And we're studying the benzophenones that are all FDA approved using your sunscreens by two different methods. So when you're looking for a molecular constant, you do experiments, and you can do them in the lab. You take the real molecule, you use the real systems, and you test it with, and you get real numbers. You can also model on the computer, and you can get theoretical and computational numbers. You can plug in your molecule to the computer, and it'll estimate where the atoms are distributed and where the electron density is. And that's how you get your molecular constants. So this pKa that I'm trying to find is it's a equilibrium constant. A K is an equilibrium constant for an acid dissociation. So when you take a protonated species, the HA, and you deprotonate it, that's an equilibrium. You can go back and forth through the protonation and deprotonation. So on the right of the deprotonated species is a free proton, or the hydrogen plus. But the pKa, is the log scale. It's the same thing you see on pH. So this H is not just floating around in solution. It's actually, it has to be accepted by the solvent, by the solvent system, and by everything that's around this HA molecule. And you can force the equilibrium to the right by adding base, because the base will actually go up to the protonated molecule and just take the hydrogen off. So we're forcing equilibrium to the right, and we're testing this acid's bond because we know which base we're adding. We have a name for this in chemistry. It's called a titration, when you add a base to test a hydrogen bond and an acidity of a molecule. So why we use two different methods to get the same number is what we're trying to get. Like Dr. Schmidt said, we're trying to go for a greener set of methods, but also if you use different methods within the experiment on the computational structure, then you can get different values. Like if you went to a football field and you try to measure with a yardstick versus a square-inch little piece of cardboard, you're going to get different values by the different methods. So here are the benzophenones and the acidic protons that we're testing their bond strength. And because they are UV absorbers, we put them in the UV spectrometer. It measures how much light these molecules absorb whatever you put in. It shines a light through and says this is how much light you absorb. But light isn't just a mass, it's broken up into different wavelengths, so there's discrete amounts of absorbance depending on the wavelength. And we can understand each spectrum by the concentration because of Beer's law, absorbance is proportional to the concentration of stuff you put in it. So what I'm doing is a spectrophotometric titration. I'm putting my UV absorbers into the spectrometer, and I'm doing a titration, which is adding base, which is testing the strength and the acidity of that molecule. So I have my OB, my UV absorber, my sunscreen in the UV spectrometer, and I take a reading, and I know that this is fully protonated, and it has a high absorbance of UV light, of the high energy, the purple light. And as I add base, I add the oxide, and the spectrum actually changes because we're changing species. So as I continue to add base, I'm watching the slow change from one species to another, so I'm testing that acidity and the bond strength until I finally get to the deprotonated state at which the spectrum are going to overlap because you're just adding base to a deprotonated event. So how do I turn this big spectrophotometric titration into a pKa? Well, each one of these spectrum corresponds to a certain concentration of base because it changes every time I take a spectrum. So if I take one wavelength, I know I have, at each absorbance value, there's a different concentration of base. So the protonated, the red line, I have a low absorbance. As I increase my base concentration, I also increase my absorbance. Now to analyze this, I use a big scary equation called the Benessi-Hildebrand equation, but it's really just a line in the sky where we have our y, our m, our x, and our p. So you see that our absorbance is in the y, and our base concentration is in the x. So what we do is we plot a straight line, and what we're looking for is that k that's hidden in the m. And so once we get that straight line, we can do a little reevaluation of this equation, and we take the m and the b out, and we can get our k by dividing the y-intercept by the slope. Now, like I said, this is a pk, so it's a much more manageable number. A negative log would turn a number like 10 to the negative fifth into a number like 5. So it's just a more reasonable number to deal with. So what we get for our pKa's of our sunscreens is around 13. We notice that dioxybenzone, the one with that extra hydroxyl group that has more solvent dependence, has a lower pK, which means it's more affected by the solvent that it's in. It's more acidic, and that bond there is weaker. To give you some context, these are some common acids that you might be familiar with, and this is their pK. So this is in a range of real molecules and molecules we're familiar with. So we're guessing that these experimental results are pretty accurate. They're in a good range. The computations is a different beast. When you do a computation, you look at free energy, Gibbs free energy. It's the delta G value that you're seeing everywhere. Delta G is a measure of spontaneity. It's a measure of free energy. It's how stable a molecule is and how spontaneously a reaction will occur. So you see that there's the same deprotonation equilibrium that we have, but instead of defining it by a K, we're defining it by a G because they're related. And because when we do computation, we get G's out. But we can't do computations for solvated molecules. We can't do them in systems already. We have to do them by themselves isolated, so in a gas phase, so they can kind of set in a little bubble and we see how they interact by themselves. We can also do solvation where we introduce a solvent to the free floating molecule, and we get delta G's out of the computer. So what we're going to do to get this delta G aqueous, which we can't find, is we're going to do things we can't do. And we're going to do the same equilibrium, but in gas phase. And then we're going to go back and forth between these, because we want to go from the left to the right on this equation to get the delta G aqueous. We take the negative solvation of the protonated and the positive solvations of the free proton and the deprotonated. And if we add those four together, we get the delta G aqueous, which we can turn into the pKa. So when we do this for just the free molecule by itself, we get enormously high pKa's. They're totally unreasonable. They basically say that the molecule is never going to give up its proton. It's way, way too unstable of a deprotonation. But this also assumes that the solvent doesn't interact very strongly with the molecule that we're looking at. So it's just kind of separate from the molecule during the deprotonation. But if we introduce a water into this calculation, which exponentially increases the time that the computation takes, we see when we do the computation that it gets pretty close to the molecule, and there's some strong interactions now. Those are hydrogen bonds, and they're some of the strongest ones you can have outside of actual connecting atoms. What we get is a major decrease from 50 to 150 in the pKa. Now that's a great first step, but this still isn't in the range of our experimental values, which were around 13. So I propose that adding 2, maybe 3 water solvents for more potential interactions, close interactions, could bring it down to the experimental values and really increase the validity of these computational methods so we can use them for real systems that we can't do the same tests on, like we do tests. So in summary, experimental methods work pretty well. We got some pretty accurate pKas out of them, but the computational methods without the explicit water interactions were pretty unreasonable. But because of the dramatic decrease in pK and the significance really increased, I propose that 2 and 3 water additions could really improve pKa values. I'd like to thank Dr. Schmidt-Key and the lab group we had. It was a really fun collaboration with them. Our chemistry staff, faculty, and fellows here is a great group of people, really fun to work with. The physics, I'm also a chemical physics major, so I've taken half of my classes in physics, and they're also a great